Hi. So the next video that we're going to go through here is just continuing with Chapter 3, Section 3, Learning Objective 2, using dimensional analysis. And what we'll do in this video in particular is work on converting between number of moles and number of particles using Avogadro's number, 6.022 times 10 to the positive 23, and also problems where the actual conversion factor is not something that is maybe a truth overall, something that is going to be hidden inside the problem. So we're going to look at two different types of problems today. The first one is, again, like I said, using Avogadro's number. And we are converting in this problem from moles to atoms. So the first thing we always do is read the question, circle the do, underline the clue. How many atoms, so the question is asking me for atoms, how many atoms are in 3.67 moles of cobalt? So then I take the number that's given to me and I write it out front. And I like to get into the habit of writing what is it moles of. Moles of cobalt, moles of water, moles of sucrose. In order to get into that habit, although it isn't technically necessary at this point, we will do problems eventually with dimensional analysis. We will be using 2, 3, 4 different chemicals in it. And so it's really important to keep track of what is what. So I just like to always write it in. You won't get marked off if you do it wrong or if you don't do it at this point, but I'm going to encourage you to try to get into that habit. So 3.67 moles of cobalt. And just as a reminder, right, you want to have this diagram out and be looking at it all the time because we're going to go through these steps again. So step number 1, at the very beginning, I guess, we kind of skipped this, but was identifying the conversion factor. For the next 4 problems, the conversion factor is always going to be the same. So we identify the conversion factor, we circle the do, we underline the clue, and we take the number that's given to us and we put it out front. Now we make a parenthesis. We put one side of the conversion factor on the top, one side on the bottom, using the principle that whatever unit is out front must also be the unit that is down below so that they can cancel out. So I'm going to put 1 mole on the bottom. I don't know if I said this before, but the word mole, M-O-L-E, is abbreviated M-O-L. That can be annoying because you're only losing the E, but you're going to write it so many times you're going to appreciate not having to write the E. What goes on the other side? On the top will, of course, go Avogadro's number, 6.022 times 10 to the 23rd. You can write the word particles down here, but, you know, we're talking about cobalt. The question asks for atoms. The particles in particular are atoms of cobalt. Now, this is what I plug into my calculator, 3.67 times 6.022 times 10 to the 23rd. And how many significant figures should my answer have? Well, this number has 3. Avogadro's number will count for significant figures because if you look up in a textbook, you can find Avogadro's number to 7, 8, 9, 10, 20 decimal places. We're only using it to 4 decimal places, or 4 significant figures, I should say. So that will limit the number of significant figures in our answer. This 1 mole is how we defined, right? Avogadro's number is equal to 1 mole, so that isn't going to count for us. So I'm going to round my answer to 3 significant figures, and I'm going to get 2.21 times 10 to the positive 24, and that's going to be atoms of cobalt. So a couple things just to take note of. Yes, this does have just 3 significant figures. My moles of cobalt and moles, those 2 units are the same so that they cancel out. And whatever your calculator gives you, if your calculator, my calculator is kind of old. So my calculator, this is what my calculator said, but I don't want to write that. I translate it back to proper scientific notation. Okay. Let's move to number 29. How many moles contain 5.73 times 10 to the positive 26 molecules of water? Circle the do. How many moles? Underline the clue. 5.73 times 10 to the positive 26 molecules right? And so if you want to abbreviate the word molecules, you can't abbreviate it MOL or MOLE because that stands for moles, but you can do MOLEC period to abbreviate the word molecules. So molecules of water, and then I make a parenthesis and I take that conversion factor that's up there highlighted in red and I put one side on the top and one side on the bottom. Again, always making sure that whatever unit is here needs to be down there. And so the molecule is a type of particle. So we would say 6.022 times 10 to the 23rd molecule is equal to 1 mole. And then I plug that in my calculator, again, using, anytime that I'm plugging these numbers in that are in scientific notation, I'm doing the second button and then the comma in order to get the small but uppercase E. And if you don't do that, you will oftentimes get a wrong answer. Again, how many significant figures should my answer have? 5.73 times 10 to the positive 26 has 3 significant figures, and 6.022 times 10 to the positive 23 has 4 significant figures. So of course we choose the least of those. So I'm going to round my answer to 3 significant figures, which is going to be 952, and that's going to be moles of water. Okay, in case you're getting not understanding, what do I mean by particles? So particles can mean atoms. Particles could mean molecules. Particles could also mean formula unit. And a formula unit is the smallest unit for an ionic compound. Okay, I'm just going to rewrite on this page the conversion factor again, which is that 1 mole is equal to 6.022 times 10 to the 23rd particles. Remember, those could be atoms, molecules, or formula units. Number 30. And at this point, if you're feeling like, I got this, pause, do numbers 30 and 31, and then check your work. And if you still have some questions, just follow along. How many molecules are there in 0.2569 moles of carbon dioxide? Circle the do, underline the clue. Take the number that's given to me, 0.2569 moles of carbon dioxide. Make a parenthesis. Take one side of my conversion factor and put it on the top or bottom, making sure that always these units out front and down bottom match. So I'm going to put 1 mole on the bottom and 6.022 times 10 to the 23rd. Which particle should I use? Well, the question is asking for molecules. Carbon dioxide exists as a molecule, so we'll put it as molecules. Now I multiply those two numbers together, and how many significant figures this time? 0.2569 has 4, 6.022 has 4, so my answer should have 4. So 1.547 times 10 to the positive 23, and that will be molecules of carbon dioxide. And the final problem with moles and particles, how many moles, circle the do, contain 2.09 times 10 to the positive 22 atoms of helium? So take the number that's given to me and write it out front. 2.009 times 10 to the positive 22 atoms of helium. Look at that conversion factor at the top of the page. Which one goes where? 6.022 times 10 to the 23rd atoms goes on the bottom, and 1 mole goes on the top. Why? Because, as always, if the word atoms is out front, the word atoms must be on the bottom. I take those two and I always multiply by the top of a fraction, divide by the bottom. So I'm going to divide those two numbers, being sure, since they're in scientific notation, doing second comma to get that small but uppercase E. And when I do that, my answer is going to be 0.03336 moles of, what is this, helium. Now, for significant figures, 2.009 has 4. Those zeros are significant because they're sandwiched zeros. They're zeros in the middle. 6.022, of course, has 4. So my answer should have 4. And remember, beginning zeros are never significant. Now we're going to do two more problems with conversion factors, but these are ones where the conversion factors aren't a known quantity. What they are sort of, I put them given in the problem itself or hidden in the problem themselves. So remember, the first step in doing these conversion factor problems is finding the conversion factor. Sometimes it's going to be a metric conversion that we've asked you to learn, 100 centimeters equals 1 meter, something that you've known from years past, like 60 seconds is equal 1 minute. Other times it's going to be something new, like Avogadro's number is equal to 1 mole. But these ones, if you read the question, you'll find the conversion factor in there. So number 32 says, an experiment requires each student to use 8 grams of baking soda. A full container of baking soda contains 340 grams. How many students can do the experiment? So students is what I'm trying to find. And then there's a lot of clues in this. An experiment requires each student uses 8 grams of baking soda. That is actually my hidden conversion factor. That one student requires or equals 8.0 grams of baking soda. Right? Those two things aren't necessarily equal in the respect that they are equal to the same thing. 8 grams of baking soda is just 8 grams of baking soda. But for each person, we will need 8 grams of baking soda. The container holds 340 grams. That's my clue. That's the number that's going out front. So 340 grams of baking soda. Baking soda is NaHCO3, or you could write the words baking soda. Now I place my conversion factor in there the exact same way that I always do. 8.0 grams of NaHCO3 for every one student. Exactly the same thing that has happened before is happening now. That my unit out front and unit down bottom are the same so that they're canceling. So in my calculator, I'm doing 340 divided by 8. When I do 340 divided by 8, my calculator gives me 42.5 students. But do I need to use significant figures in this case? Well, am I measuring students? What instrument did I use to measure a student? I didn't. Can 42.5 students do the experiment? There's no such thing as 0.5 of a student. So I have to choose. Is it 42 students or 43 students? 43 students couldn't do this. So even though it's 42.5, this is where you have to think a little bit. And in fact, only 42 students can do this experiment. And then the last one on this page, again, if you want to give this one a try on your own, pause it. If not, we're going to continue. Each page of the yearbook can hold 20 underclassmen portraits. That's my conversion factor. Page, 20 portraits. So I'll write that down here. One page equals 20 portraits. If there are 159 freshmen, 163 sophomores, and 190 juniors, how many pages will we need for this section of the yearbook? So the first thing I'm going to need to do is to figure out how many total students there are. So I'm going to take 159 and 163 and 190 and add them up, and I get 512 students. That's the number that goes out front. 512 students. Now our conversion factor says one page equals 20 portraits. Could that also be one page is equal to 20 students? Sure, because each student just has one portrait. So I'm going to put into my conversion factor one page for every 20 students. And again, I do the calculations. What do I get? 25.6 pages. But this is a book. A book doesn't come in a half a page or 6/10 of a page. It has to be whole pages. So now I have to think logically. Is it 25 pages or is it 26 pages? And yeah, in fact, it's 26 pages.